Let's introduce the concept of momentum. We've looked in previous presentation of the equations of motion and the laws of motion developed by Isaac Newton, and the concept of momentum is also associated with Newton and the development of his laws of motion. Momentum is a measure of the quantity of motion that a body possesses, and a body in this context could be a car, it could be an aircraft, it could be a football, etc. Momentum is defined as the product of mass and velocity. So in other words, momentum is equal to mass multiplied by velocity. In symbol form, momentum capital M is equal to mass lowercase m multiplied by v for velocity. Just be careful in this work, we'll be using the uppercase and lowercase m's to signify momentum and mass respectively. So make sure your calculations clearly define the upper and lowercase m's as required. Exercise 1M, considering the momentum equation, it can be shown that momentum is a vector property. And as we know from previous work, a vector has a magnitude, a size, and a direction. And just as we considered force balances in previous lectures on laws of motion, we had to take into account the direction of the forces. So in this case, because momentum is a vector property, we also have to be very careful about the direction in which we are considering momentum. And as we did with forces, we will have a sign convention to state the positive direction in the various calculations we're going to undertake. Exercise 2M, we've got to state the derived units of momentum. Well, as with all quantities in the SI system, we obtain the unit from the equation. So as momentum is defined as mass multiplied by velocity, then mass in the SI system is the kilogram, velocity is the meter per second. The unit of momentum is the kilogram meter per second. Notice the unit for momentum could also be stated as kilogram meter second to the negative 1. Just another form of kilogram meter per second. Exercise 3M asks us to consider the alternative form of momentum unit, the Newton seconds, and show its equivalent to the kilogram meter per second. So to show that the Newton second is actually the same as the kilogram meter per second, if we know that Newton in the SI system is actually a kilogram meter per second squared from its definition, and we multiply that by seconds, we can clearly see that the second on the top cancel with the seconds squared on the bottom to leave us kilogram meter per second. So we can see that the Newton second is equivalent to a kilogram meter per second. So you can either state your unit of momentum in terms of kilogram meters per second or in terms of the alternative unit of Newton seconds. The choice is yours. They are often freely interchanged in calculations. Exercise 4M, we're asked to calculate the magnitude of momentum for each of the following questions. Questions A through to D. They're all based on using the equation momentum is equal to mass multiplied by velocity. Just be careful in some of the questions. The mass is in kilograms and the velocity is in meters per second. The same with the second question. But notice in the third question here, part C, the mass is 1 megagram. And this is the fourth question here, part D, the mass is in tons here. And also the velocity is in kilometers per hour. So be very careful with your conversions there. I'd encourage you to stop the presentation and attempt those 4 little questions. The answers are shown in the brackets on the right hand side with various units stated noted. Exercise 4M, here are the solutions to the questions. I'm sure you're able to work them out for yourself. Just note that the 1 megagram is equivalent to 1,000 kilograms. And of course the 40 ton is equivalent to 40,000 kilograms. Also notice that the 60 kilometers per hour was converted into meters per second, which was 16.6 recurring meters per second. Here is the calculation for working out the kilometers per hour. We reviewed this calculation in previous presentations. To convert from 60 kilometers per hour, we have to multiply by 1,000 divided by 3,600. In this case, the velocity is 16 2/3 meters per second. Exercise 5M, if the momentum of a 10 kilogram mass is 25 kilogram meters per second, we've got to calculate the velocity. So again, using the equation, momentum is equal to mass multiplied by velocity. We have to rearrange the equation to find velocity. Again, I'd encourage you to attempt this question. The answer is shown here in the brackets, and the full solution is shown on the following slide. So here's the solution for exercise 5M. So the momentum in this case was 25 kilogram meters per second. That's the momentum of our mass. Mass was 10 kilograms, shown here. And we've got to calculate the velocity. So from the equation, momentum is equal to mass multiplied by velocity. We just transpose, divide both sides by little m. Velocity is equal to the momentum divided by the mass. Inserting the values, calculating, the velocity is 2.5 meters per second. Here are some tutorial questions related to momentum. I'd encourage you to attempt. So question 1M, we're asked to determine the momentum of a drop hammer having a mass of 0.5 tons when its downward velocity is 7 meters per second. The answer is shown here in the brackets. I'd encourage you to attempt this question. Solution shown on the following slide. Here's the solution for question 1M. Just be careful, the mass was stated as 0.5 ton, so of course that would be 500 kilograms. Question 2M, a milling machine table and its component have a combined mass of 350 kilograms. We've got to calculate the momentum of the table plus its component when the feed rate, the speed of the table, is 300 millimeters per minute. Again, it's just a question of calculating momentum as we did in the previous question, but be careful with the feed rate because the velocity here is in millimeters per minute, so you need to convert that to meters per second. Again, the answer is shown in the brackets. I'll encourage you to attempt this question. Full solution is shown on the following slide. Question 2M. We have to calculate the momentum for the table on the milling machine, and given the mass of 350 kilograms and also the feed rate or the velocity of the table, 300 millimeters per minute. To be careful with the conversions, to convert 300 millimeters per minute into meters per second. So first of all, we have to divide by 1,000 because that converts the millimeters to meters. Then we have to multiply the denominator by 60 because that converts the minutes to seconds. So evaluating the velocity is actually 0.005 meters per second. From there we can work out the momentum from our standard formula, and that's 1.75 Newton seconds, or 1.75 kilogram meters per second. Question 3M, a sliding member on a machine tool has a mass of 250 kilograms. We've got to determine the momentum change when the sliding speed is increased from 0.005 meters per second to 0.04 meters per second. It's just a question of working out the change in momentum, so work out the initial momentum and then the final momentum and take one from the other to get the change in momentum. The answer is shown here in the bracket, so I'll encourage you to attempt this question. Full solution shown on the following slide. Question 3M. So here's our sliding member, has a mass of 250 kilograms. The initial velocity, I've called that U here, is given as 0.005 meters per second. And the final velocity I've called V here is 0.04 meters per second. So to work out the change in momentum, it's simply going to be the final momentum, m multiplied by V, subtract the initial momentum, m multiplied by U. All I've done here is factorised because m is common to both terms, so m outside the bracket and then the v minus u inside the bracket. Inserting the numbers and evaluating the change in momentum, the answer is 8.75 kilogram meters per second. Question 4M is slightly more complicated. An 80 kilogram rocket has achieved its maximum altitude and it begins to descend to Earth with gravitational acceleration. If the rocket takes 9.3 seconds to impact the Earth's surface, we've got to calculate the velocity and the momentum on impact. There is a hint in the question to use an equation of motion to calculate the velocity of the rocket on impact. So this question refers back to our work on the equations of motion, which we reviewed in a previous presentation. If you think you can attempt this question without further assistance, I'd encourage you to start the presentation. The answers are shown here in the bracket on the right hand side, but the full work solution is shown on the following slide. This is a solution to question 4M. So we need to be careful with the information in the question. There's an 800 kilogram rocket, so mass is 800 kilograms, and it reaches a maximum altitude. Now we need to understand that at maximum altitude, the velocity of the rocket, I've shown as u there, is 0. So at maximum altitude, the rockets are just about to start to fall to Earth, so it must have 0 velocity as it moves from upward motion to downward motion. So my u, my initial velocity, is 0. We're told that the rocket takes 9.3 seconds to impact the Earth, so my little t is 9.3 seconds. We've got to find initially the velocity on impact. So what's the velocity as the rocket hits the ground? Now we need to do a little bit of thinking here. We know that the momentum is equal to mass times velocity. So at the moment, the only thing we know about the equation is we have the mass. We do not know the velocity on impact, v, and we do not know the final momentum on impact, m. But if you remember back to our equations of motion we looked at previously, one of the equations, which is useful here, is the v equals u plus at equation. Because in this equation, we know the initial velocity, it's 0 in this case. We know the acceleration, because in the question, it says the rocket falls to Earth under gravitational acceleration, so that would be 9.81 meters per second squared. And we're also given the time in the question of 9.3 seconds. So we can calculate the velocity on impact, and of course from there we can calculate the momentum from our equation above. So that's my thinking process through the question. I'd encourage you now to attempt the rest of the question. The full solution is shown on the following slide. So exercise 4M, solution continued. First of all, we're going to find the velocity v. I said we do that from our linear motion equation, v is equal to u plus at, and the velocity calculates to be 91.2 meters per second. So that's the velocity on impact with the ground. Part 2, to calculate the actual momentum on impact, we use the momentum equation. We know the mass is 800 kilograms for the rocket. We've worked above the velocity on impact, 91.2 meters per second, so we can calculate the momentum. It evaluates to 72.96 kilonewton seconds in this particular case. Question 5M, we're asked to calculate the magnitude of the total momentum for the 15 kilogram machine component shown in the sketch here, and also the components of the momentum in the x and y directions. Notice the positive senses of x and y shown here. The hint in the question is to use basic trig to calculate the components. Notice the velocity v is stated in the question, it's 2 meters per second. Also notice that the direction of the velocity and indeed the momentum is 60 degrees to the horizontal. If you think you can attempt this question without further assistance, I'd encourage you to stop the presentation and attempt it now. The answers are shown here in the brackets. The first answer is a total momentum. The second answer is the momentum in the x direction. Notice a negative sense. And the third answer is the momentum in the y direction. So solutions for question 5M. Extracting information from the question, the actual mass of the machine component is 15 kilograms. Its velocity is 2 meters per second at an angle of 60 degrees to the horizontal. So the first thing we can do is to calculate the momentum at that angle to the horizontal. So step 1, find the total momentum of this machine component. So momentum equals to mass multiplied by velocity. So it's 15 kilograms multiplied by 2 meters per second. So 30 newton seconds is the momentum in this direction shown here. Here's the calculations for the x and y components of momentum. Part 2, to find my. I'm sure most of you will see that the function you're going to need to calculate my will be the sine function, because I'm given the angle and I'm given the hypotenuse side of my triangle. But if you're not sure, you can always use a SOHCAHTOA mnemonic, which we mentioned in a previous presentation on basic trig. And you'll find that the sine of the angle, 60 degrees in this case, is equal to the opposite side my divided by the hypotenuse, which is 2. Rearranging and evaluating the momentum in the y direction is 26 newton seconds, and that's a positive y direction, as it's in line with the positive y notation shown in the question. Step 3, we now calculate the mx component. Again, for my basic trig, that's the cos function, so cos of 60 degrees is mx divided by 2, and again rearranging for mx, component of momentum in the x direction is 30 multiplied by the cos of 60 degrees. That's 15 newton seconds, and that's shown in this sense from left to right. So notice the answer in the question is a negative 15, and that's because our component is going from left to right, but the positive notation for x is shown as right to left. So the magnitude of the momentum component in the x direction is 15 newton seconds, but its actual value is negative 15 in the answer. So question 5 was trying to emphasize the fact that momentum is a vector quantity, so you have to account for its direction in your calculations. Here's the bibliography used to help generate this presentation.